We're going to be covering Chapter 3, Section 11. This is thin-walled tubes under torsion. When we're talking about thin-walled tubes, we have a shape or a tube that doesn't necessarily have a circular shape, but it has some other shape associated with it. And this tube is under torsion. Here we have a torque on both sides. And this tube is going to be twisted. Now, when we look at the cross section here, so I'm just going to draw this arbitrary cross section again, it is going to be what we call thin wall. So the thickness of our wall, T, to our overall diameter, D, the thickness has to be much, much less than the overall diameter. Now, we're going to get into discussing how do we analyze this type of problem. And what we can talk about with this type of problem, we indicate that there's a thickness T here, but across this cross section, T can vary. So the thickness around the cross section may not necessarily remain constant. It can change. But when we look at that thickness along the whole entire length, that thickness will remain the same. So along this direction, the thickness will remain constant, although as we change around its circumference or around its perimeter, that thickness can change. So let's take a look at how we were going to analyze this. Well, if we have a section here, I'm going to just draw this out here. We're going to have a section here, dx, that distance dx. And that dx, I'm going to create just one little slice out of this entire object. So I'm going to take this, I'm going to redraw it here. And if we draw this, we have a face here. And I'm going to try to exaggerate this, that it shows that the thickness can change in this direction. So if we look at the book, this is labeled as A, point B, point C, point D. And this thickness, we have a thickness here, which is going to be called T. We're going to call this TC. And the thickness here, which is going to be considered T sub B. Now, on this face here, we can look at it and we can tell that there's going to be a shear stress. With this torque that's being applied, this torque is going to create a shear stress on here. So in this case, we're going to end up with a shear stress here, tau, and we're going to call this tau. Well, actually, this one is going to change. So let's label this up. So this is going to be, we're going to call this tau B. This is going to be tau C on this side. And these are really going to change from tau B to tau C. So this is going to change from tau C to tau B. So it's really changing on these two end sides. But if we look at the total area, because the area is going to vary uniformly along the length in this direction, those taus are going to remain constant. Or they're the same on both sides. They're just opposite directions here. But if we take a look at this, we can really say that those shears have I'm just going to redraw our element here. We can say that we have a force. So this tau really can be translated into a force, what we call F1. This one is F1. It's equal and opposite. And then we have our other two forces here, FB and FC. So if we take a look at this, F1 is equal and opposite. Those are going to cancel out. And FB and FC are in opposite directions. So we know that our FB must be equal to our FC. Now, what we need to do next is take a look at how do we calculate FB. Well, the force on that face here is going to be related to our shear stress on that face. So we need to know that the shear stress, FB, times the area on that face. So the area on that face is dx. dx is the length times its thickness, T sub B. T sub B. So we have shear stress times, this is our area, and we end up with a force. F sub C is the tau on face C, so that's this over here, times our area, dx, times our thickness of that surface C. So we have, again, tau C times that area gives us that force. Now we have our equation here. We can see that dx's are the same on both sides. And we end up with tau B times TB times the thickness at B, and tau C times TC are going to be equal. Now, what does this indicate? This indicates that when we look at a cross section, and the shear stress is going to be related to our thickness. And in this case, we're going to have a term called F, and F is going to be tau times T. So the shear stress times the thickness, and that is going to be remain a constant. And in this case, that is called shear flow. And this is the concept of shear flow. So thin-walled tubes under torsion, we are going to end up with having a shear flow constant, which we'll be able to calculate, and we're going to use that for our future analyses here. Now, the one thing to notice here is that the shear stress is maximum in a cross section at the minimum thickness. So max shear stress, tau, occurs at minimum thickness. Okay, so with this concept, we're now going to use this and start calculating our torsional formula. So I'll try to leave this up because we're going to use some of these concepts again. So again, thin wall tube, and we're going to be talking about the torsional formula. Now, I'm going to redraw our cross section here a little bit, and what we're going to do is I'm going to draw a little bit thicker just so we can see it a little bit better. If this is our thin-walled section, one of the things that we're most interested in is this midline, so the line right in between the inner and outer surfaces. Or if you think, it's really the average of the thickness. There's a length of a line that's an average thickness. And that's what we're going to call the median line. Now, when we look at the analysis, we're going to really use this median line a bit. And if we look at the length of that, so let's say we have a starting point. We can have some starting point here. And if we go around that median line, we're going to talk about distance S. And what I'm going to do is I'm going to show another little section right down here. So I'm going to just take a little bit of this and call this DS. So that DS is a small section of our around our perimeter. Now with this DS here, we can look at kind of this point O, and we can look at the total force that's acting on just this small surface. So this force is acting, and if that force is acting on that little area, and we come up with a perpendicular distance here from our point O, we can, and that has a perpendicular distance r, we can look at what is the torque that this little cube or this little section is applying about 0.0. So that first, let's look at the force. Force on this section is equal to F, that's our shear flow, times ds. So shear flow times ds is going to give us a force. Now, if we look at what is the torque that's just being created by that, we're going to call that dt. So that's just a part of the whole cross section. So the torque that's generated by that section ds is going to be equal to our radius, that's our distance, times our force, which is F times ds, right there. So now we have our incremental torque equation. Now to figure out the total torque that's acting on that entire system, cross section, total torque, we need to integrate dt over the entire cross section. And in that case, we're going to end up integrating from 0 to the total length mean. So that's the entire length of that median line, times our dt, which is our r f ds. And when we do that, the torque is going to be equal to F, which is going to remain a constant, integral from 0 to our length of r, because our r is going to change, and our ds is going to be our incremental length. Now, when we do this integration, this portion right here, I'm not going to go through all of the math here, but we can say the integral from 0 to Lm of r ds, that is going to be equal to 2 times the area mean, where Am is area mean. Now, what is that? That is this entire area inside that median line. So, if we can identify that median line, we can calculate the entire cross-sectional area, not of just our thin section, but of the entire section there. And that we're going to use as 2 times our area mean, and we're going to plug this in. And what we end up with is T, our total torque, is equal to our F, our shear flow, times 2 times our area mean. So this is going to be one of our equations that we're going to end up using. Now, we're not necessarily just interested in our torque. We ultimately want to come up with what is our shear stress. So how do we come up with our shear stress? We can rearrange this equation and solve for F. F is going to be equal to our torque divided by 2 times our area mean. And we know that our shear flow, F, is also equal to our tau times our thickness. Now we can equate these two together, and we're going to solve for our tau. So in this case, we get tau is equal to T, our torque, divided by 2 times our thickness times our area mean. Area mean. So this is our shear stress equation. So if we have a thin wall, a section, if we know the torque that's being applied to that section, the torque, we know the thickness at any point in that section, and we know the area mean that we can calculate up our shear stress. So let's take a quick look at one example. Well, this one we already know, but if we look at just a circle, let's say the circle has an average radius of r, and it has a thickness of t. Our area mean is going to be equal to pi r squared. It's just that cross-sectional, or that area equation for that circle. So if we go and write up our torque, or our shear stress, is equal to our torque divided by 2 times our thickness times our area mean, which is pi r squared. And this would be our shear stress equation for our thin wall circular or hollow circular tube. So torque, thickness, radius gives us our shear stress. We can also do this for rectangular cross sections. So if we look at a rectangular cross section, again, this is a thin wall rectangular cross section. And if I take a look at the vertical sides is going to have a thickness of T1. The horizontal sides are going to have a thickness of T2. From our midline here, we can call our distance on the bottom the base. And from our midline on the top and the bottom, we're going to call this our height. Again, this is from the midline or the median line through that section. That's important. So again, let's take a look at our area mean. Area mean is going to be just our base times our height. And now we can come up with 2 different torques, because we can have a shear stress in the vertical section. And the shear stress in the vertical section, we're going to use our equation, which is torque divided by 2 times the thickness. And in the vertical section, we have T1, so this is going to be T1, times our area mean, which is B times H. And then we can also look at the shear stress in the horizontal, which is the torque divided by 2 times T2 times B times H. So now we have our 2 shear stresses there. Again, we would want to take a look at these and determine which one is greater to determine our maximum shear stress. Obviously, the thinner thickness is going to create that larger shear stress. So next we're going to talk about torsional constant. We've talked about torsional constant in the past. This is our J. We've used this in multiple equations in the past. And if we take a look at the definition, now the book will go through and do the total derivation, but I am just going to give us our J equation. So our J equation is going to be 4 times our area mean squared divided by the integral from 0 to L mean of ds divided by t. So this is our definition. Again, I'm not going to go through the derivation, but if we take a look at a circle, or this thin-walled circle section, we will find that our J turns out to be 2 pi r cubed times t. For a thin wall rectangular section, where we have T1 and T2, same values as we did previously. J is going to be equal to 2 base squared height squared T1 times T2, all divided by base T1 plus height times T2. So now we've got different J's, different torsional constants for different values, or different geometry shapes. Well, what can we use that for? Well, let's take a look at it. We can look at our shear strain. Our shear strain is going to be defined as T squared L divided by 2GJ. We can also look at our phi. That's going to be equal to TL over GJ. This is our torsional equation that we've used in the past to determine rotation. So it looks exactly the same, we just need different J values. And again, when we look at this, the denominator GJ is still our torsional rigidity. That takes care of section 3.11.